Welcome to Probabilistical Graphical Models. This encompasses Bayesian networks and Markov networks. My name is Jose Calis, and I'll be the person who is going to explain you about these weird models that nobody talks about, but they are really interesting, just in case. So the outlines of the presentation will be first the introduction, then we will talk about some of the Bayesian networks, Markov networks also. For those who are interested in these topics, I'll give you some good information you can check in the next steps, the bibliography, and later we're going to see an example in Python. So let's start. Introduction. So probabilistical graphical models, PGMs, are just a structure to represent conditional dependence. We have seen, for example, in the naive base, that the first assumption we did was to say that all the variables were independent each other. Sorry. Well, this is not the case of the reality. We know that some variables are dependent on the other variables, and probabilistic or graphical models are a way to represent this dependence and to get at least some more realistic values of the classification. PGMs confirm the idea that the graphs are the utility to represent complex models. We have seen, for example, in the neural networks or super vector machines, basically, even though that we understand the notion of the classificator, in the end it's a black box. You have some inputs, you have some outputs, and that's it. And it's not really intuitive to understand what is happening in between. The goal here will be to capture the joint probability distribution of the random variables. Okay. So we have here, this is a toy example. In this toy example, basically we have a classroom. And in this classroom, we have some random variables, which are difficult, intelligence, the score the person got in the SAT, the grade they got, and if they got a recommendation letter or not. We have seen here, for example, that the grade, this note here, depends on the difficulty of the class, I'm going to write an arrow here, and also in the intelligence, in this sense, the arrow. Also, the difficult columns, the influence might go here, and difficult can influence if the person got a letter or not. One might think, for example, if we want to classify if there is a recommendation letter, why do we have the SAT? What is the point of having a node that is not connected straight to the class we wanted to classify? Well, we'll see later that the influence might go in this way, for example, if we know some values. So that will be just interesting on how we understand the data that we're trading. So let's continue with this. Bayesian networks. So in Bayesian networks, we have random variables, and we're going to stick to the toy example where we had difficult, intelligence, grade, SAT, and letter. And the idea is to capture this joint distribution. In the naive Bayes model, we had that the joint distribution was just a multiplication of all probability distribution of the random variables. This is not the case. As we saw before, we have dependencies. So the joint probability distribution will be the multiplication of the variables that are independent, which we saw that are difficult and intelligence because they are in the top of the graph, or basically they don't have any parent above them, and so we will they are the independent random variables, and we have seen that all other variables depend in some way or the other to these two initial random variables. So if we apply the chain rule, you will get that the joint probability distribution will be just to multiply the two random independent variables and all of the dependencies that are in the graph. For example, grade was dependent of difficult, which is here, and intelligence, that is here. All right, so let's keep going. In this third example, I have collected all the information that we need to parameterize our Bayesian network. So in these boxes, you have all the probability distributions of the nodes. Here we see that, for example, difficult and intelligence they only have two values. We're going to treat them as binary for now because it's easier to understand. But they don't have any dependencies on all other nodes. Well, for example, SAT here have a dependency of if the person is intelligent or not. 0 basically means the person is not intelligent, while I1 means that the person is intelligent. The probability of getting a person that is intelligent is 0.3, and the complement is 0.7. Just keep in mind that this sum of the rows has to be always 1. Okay? So, for example, here in grade, this sum in this direction or the other way, this has to be equal to 1. So for the SAT, we have that, for example, if the intelligence is 0, the probability of not nail the SAT is 0.95, which is something according to the reality. The more intelligent, the better are the scores in this kind of tests. The grade, for example, if the person is intelligent, which is this case, and the difficult is also high, the probability of getting a good grade is 0.5. In this case, G1 stands for the good grade. G2 somewhere in the middle, and G3 not something good. Probably the person not approved the requirements for the class. So what will be the highest probability of getting a good grade? Well, if the person is intelligent, here this will be the case. If the person is intelligent and the class is simple, there's a high probability, 0.9, of getting a good grade. Now, what happens with letter? Even though the difficulty influences grade, why does difficulty not influence letter? Actually, it does influence, because if the difficulty is low, probably the grade is going to be higher, and probably the letter will be better. But in this graphical model, we see here that we only have the grades that are conditionally dependent the letter. So if, for example, a person got a good grade, which is G1, and the probability of having a letter is 0.9, which is high, which makes sense. So if the person didn't got anything good on his grades or she's grades, on her grades, probably it won't get a recommendation letter. So that is why the probability of not having a letter, given that the grade was bad, is 0.99, which is really high. So this is just a Bayesian network with the conditional probabilities. We're going to use that later if we want to classify something. We say that P, which is the conditional joint probability distribution, factorizes over G. Here G is the graph. The graph we were seeing in the lines above. If we can use the chain rule to get the joint probability distribution. So we saw here in this equation that the conditional probability distribution will be this probability of difficult